you think that you can run away from quantum physics by going to a scale where it doesn't matter. So in the scale of planets, black holes, where gravity takes over. But no, because what happens is that for a lot of our experiments with gravitational waves, we use interferometry. First of all, there's light involved already. So light, which has very strong wave properties, means that it's under the rules of quantum physics. So the more an object has strong wave properties, the more it has to follow the rules of quantum physics. And one of those rules is the uncertainty principle. With using light in interferometry for gravitational waves, you start with your light source and then it hits a piece of mirror and then it gets split into two perpendicular directions. What happens is that at the end of the path of those two light beams, there's a mirror and it bounces back from that mirror and then comes back to its source and then it hits our detector. If a gravitational wave passes by space-time, and what happens is that the distance between the starting point and the mirror, it changes, it shifts. So that's why we use two perpendicular directions, so that if a gravitational wave it passes by, you can see a shift in those two directions. Maybe there's more in one direction and then there's less in the other one. That's the setup. So the important quantity is that distance, as I was saying before. So if that distance changes, we know that, okay, maybe a gravitational wave passed by. And depending on the amount that that distance changed, we can quantify more about the source of this gravitational wave passing by. This distance is really important. So with the uncertainty principle, what happens is that with the light that we used, we can be really specific with its position, because this is important to know the distance. And if we get too specific with this position, we become less specific with the power of that light. So this piece of light, it's a wave, it has an amplitude or a kind of height. We're trying to be specific with the position. What happens is that that piece of light, its amplitude changes up, for example. This ends up being noise to our detectors. We don't want this noise, because the thing is that the gravitational wave that we detect, they're already really low frequency, or they're really faint signals. So if there's even a tiny bit of noise because we try to be too precise, then it makes all of your measurements kind of fucked up.